Today's lesson is about compositions of isometry. Really, composition just means a combination of more than one. Remember also that isometry means any sort of transformation that does not change the shape of the figure and creates an image of the original that is congruent to what you started with. So, quick recap of all the different types of isometries you learned. There's translations that slide a figure into different directions. There's reflections, and there's rotations. You also learned at this point one type of transformation that is not an isometry, and that's the one that changes the size of the figure with enlargement or deduction in terms of dilation. When you're combining multiple isometries, the composition or combination of two or more isometries at once is still an isometry. In other words, if you do two different types of rigid motions, like you do a reflection and then you do a translation, the end result will still be congruent to your original shape. Now, for each type of translation that you do, you add another prime symbol, almost like an apostrophe, but not quite, to the name. So if you see something like A double prime, B double prime, and so on, it really means that it took two different transformations to get to that result. First theorem. Theorem 9.1 says that a composition of reflections across two parallel lines is a translation in the end. So draw your two parallel lines and look what happens when you take this triangle and reflect it over the first line. And take that result and do a second reflection. I want you to notice that we could have gotten to the same end result, the same image, by just taking the original pre-image and doing a translation, a slide to the right instead. That's what theorem 9.1 says, that anytime you do a double reflection over two parallel lines, the end result you could have gotten there just as easily by doing a translation. Notice how it only works with parallel lines. If you have lines that are not parallel that intersect at some point, then you cannot get to the end result by doing a translation. Now, you're going to notice that the notation of composition of isometries, you always do the second or the inside one in the parentheses first. So here we have triangle ABC, and it's saying first reflect triangle ABC over line L, and take that result and reflect that over line M. So step one, reflecting over line L. You measure the distance of each vertex to line L, and then to do the reflection, go the same amount of distance across line L. That's step one. Next, you do the reflection of that result over line M. And there's your final result. Part B, what is the distance of the resulting translation? Well, you could get to the same image, the same end result, just by taking the original triangle and sliding it up 8 units. So you could say it's a translation of 8 units as well. Theorem 9.2. The composition of reflections across two intersecting non-parallel lines is actually going to turn out to be the same result as a rotation around the point where they intersect. So this is what happens where instead of reflecting over two parallel lines, you reflect over two intersecting lines. First reflection, second reflection across the other line, and here's where it gets interesting. I want you to notice how you could have gotten the same result by taking this triangle and rotating it. Think of spinning it like a pinwheel, and it would end up facing this direction instead. So now we're going to practice that. Here we have two intersecting lines, L and M, that are 60 degrees apart, and we're asked to do a double reflection of this figure, which is really just a letter F. What is the image of F reflected first across line M and then across line L? So when it's not in a coordinate plane, it gets a little bit tricky because you have to eyeball it. If you have a ruler, it helps quite a bit because it can help you keep track of distances to each line of reflection. So first, you would measure the distance of 2 points on your letter to line M. Now the shortest distance always makes a right angle to your line of reflection. So I would maybe line up the edge of your ruler so it's flat, making a right angle to measure this distance and this distance. And then to reflect it, you go the same distance across the line. So after your first reflection, F should be right around there. Now for the second reflection. If you measure the distance from 2 points on your letter to line L and go the same distance across the line, your image is here. Second part of the question, what are the center of rotation and the angle of rotation for that result? Because remember, your last theorem says anytime you do a double reflection across two intersecting lines, you could really describe that result as a rotation. Well, we know the center of the rotation is a point where the lines intersect. That's what the theorem said. So point P is the center of rotation. Go ahead and draw lines to connect your original pre-image with your last image to the center of rotation, point P. Now here's how you can calculate the angle of rotation. You can actually take the degrees between line M and L here and double it. It's a 120 degree rotation from the original F to your end result around point P. Here's a logic of why we could just take the 60 degrees and double it. So first off, you know how with reflections, the angle here and here would match? Let's say the 60 degrees was split into 20 and 40. We don't know what it's split into, but let's just pretend. We know that it's split into two angles here and here that add up to 60 degrees total. So if this is 20, then this section is 20. If this is 40, this section is 40. In other words, in whatever degree sections the measure of this 60 degree angle split into, each piece will be doubled by the reflections. So why not just take the whole combined 60 degree angle and double it? And that's a shortcut that will help you a lot on the homework. A glide reflection is a composition of a translation and then a reflection across a line parallel to the direction of the translation you started with. So let's say you have a triangle like ABC here. If you first did a translation in a line parallel to that line of reflection to the right, you'd have triangle A prime, B prime, C prime. And then if you did the reflection across that line, your image would end up here. Triangle A double prime, B double prime, C double prime. And that process would be called a glide reflection. Number 3, what is the image of triangle RST with vertices listed for a glide reflection where the translation that you do first is really just adding 8 to the x half of each vertex and the line of reflection is at y equals 0. So it's a glide reflection, so you do the translation, the slide first. There's two ways to solve this. One is to graph, and the second is to figure it out without graphing, which is what we'll talk about here because it's a good shortcut to know. First off, take your vertices, and then for the translation, just add 8 to the x half of each point. Now, to reflect across the line y equals 0, think of y equals 0 as really just the x-axis. If you make a reflection over the x-axis, it just takes all your points, and it doesn't change the x half of the point, but it changes the y half of the point to the opposite sign version. So 3 comma 4, when it reflects over the over the x-axis, becomes 3 comma negative 4. 6 comma 3, when it reflects over the x-axis, becomes 6 comma negative 3, and so on. So those are the vertices of your image. Now, when they ask you to graph a composition of isometries, it's important to start with the one on the inside first. So here we have a translation of 2 units right and 3 units up. So you'd go ahead and take each point, point C, point A, and point B, translate them 2 units right and 3 units up. Then you would draw the line of reflection so that you're able to reflect it over x equals 2 next. So find x equals 2, that's a vertical line. The closest corner of your triangle to your line of reflection is 1, so that's how far that point would reflect across a line of reflection. So that triangle is your image. Pause here and try question 5 on your own. So first you draw the line of reflection at x equals 1, a vertical line, and you'd reflect your original triangle across that. Your second line of reflections is at y equals 0, which is the same thing as the x-axis. So there's your final result. Part B, what is the angle of rotation of the result? So go ahead and connect point C and C prime or C double prime to the place where your 2 lines of reflection intersect, because that will be the center of rotation. So if you draw it, see how it makes a straight line? So you could visually tell that it's a rotation of 180 degrees. It's like having a pinwheel and spinning it halfway around the circle. Visually, that's how you could tell. In terms of using that equation, that you could just double the angle between them. See how the angle here between your blue line of reflection and your pink line of reflection is 90 degrees? You just double that. 2 times 90 is 180 degree rotation around this point. That's it for today, guys. Don't forget to turn in your notes on Schoology when